Mario Milazzo is an assistant professor at the University of Pisa. He got a master's degree in mechanical engineering and a PhD in biorobotics at the Scuola Superiore Sant'Anna, prestigious public research university in Pisa. His research interests cover many fields, including multi-scale modeling, mechanics, biomaterials, mechatronics, and industrial robotics. He has received 3 years Marie Curie individual scholarships in collaboration with the Massachusetts Institute of Technology, USA, and he has been involved both as project manager and team leader in various projects with national and international companies such as General Electric, Membro, Magneti Manieri, and Piaggio. So, now I leave the floor to Mario for his presentation concerning collagen-based inks reinforced with hydroxyapatite nanoparticles for 3D printing, a rheological study comparing bovine and fish sources.
Thank you very much for your nice presentation. Thank you for having me. So I don't have a big overview of topics, so I'm going to the details of a bunch of results that we have just got, and this is a work that we have started at the beginning of March when I joined University of Pisa. So this work was basically carried out at the Department of Civil and Industrial Engineering in collaboration with Professor Seggiani and Serena Danti and Professor Gallone, and in collaboration with our technician Irene Anguillesi. First of all, if it works, okay. Why collagen-based inks? So for 3D printing. So our framework is something related to the replacement of organs and specifically tissues and bone. Because as you know, collagen is one of the components of bone at the atomistic scale. Here you can see the hierarchical structure of bone. So starting from the macro scale that we know, the scale of centimeters, we go to the osteons, fiber pattern, fibers, mineralized for to the microphone. Okay, I'll try to speak loudly and closer to the microphone. Okay, you see here mineralized fibrils, and at the basis of mineralized fibrils we have collagen, hydroxyapatite, and water. So this is the reason why we want to study collagen. But here another question. Okay, not too much. It doesn't work. Okay, the video doesn't work, but all you know that collagen. Okay, now maybe, yeah. Collagen, no, it's working. Okay. Collagen is one of the matrices that usually are employed to 3D print scaffolds for tissue engineering, and is among all the others, alginate, chitosan, PVA, silk, and etc. These are the soft matrices because we have also the hard matrices are basically PCl, PVA, and so on. Why we need something related to collagen and hydroxyapatite? We need it because we want to create a composite, hopefully also with cells, in which we have specific structural properties with a balanced resistant toughness at the macro scale, but also with an improved rheology in order to stabilize the printing process. And eventually also specific biological properties, both in vitro and in vivo when we are carrying out studies like this. So collagen, where can we find collagen? Most of all, human sources. But all we know that the human source is very expensive. So this is why here I'm doing this presentation, since we are speaking about green chemistry, because otherwise. So collagen from marine and bovine sources. So they're much cheaper. We can extract collagen from the waste, from marine and bovine wastes, and we can use the sources to create, to get the peptides mixed with the hydroxyapatite and create the inks in order to create a prosthetic device that can be used in the medical field. So the objective is to correlate, again, okay. The The objective is to somehow correlate the rheology and the printability of animal-based collagens for bone tissue replacements. And this is why, and the reason behind this is because usually we try to print collagen and hydroxyapatite in fixed compositions. Usually it's much more filler than the matrix, so the amount is usually 90-10 in weight, but without a precise and tuned, let's say, composition. Again. Okay, so as for the materials, we collected collagen from a local source here, a company, Lapi Gelatine, and these are peptides with a molecular weight in the order of 2 kilodaltons. So we don't have the complete structure of collagen, we have just peptides. So this is something different with respect to the usual treatment of collagen. And we are using hydroxyapatite with diameters, it's a powder, with a diameter that is less than 1 micrometer. And we are not using the nanometer scale hydroxyapatite because we observed in previous studies that the printability is not so good. So we saw in previous studies that the hydroxyapatite with diameters, let's say, a little bit bigger are better. As for the preparation, we gently mixed the powders and we added the acetic acid in the composition is 1.7 to 1 to 1. And we got this very nice paste inside this beaker. And we observed, and we tried to observe, the rheological parameters using a plate-plate configuration with the rheometer. So you can see here it's a scheme, but we are using, let's say, a standard rheometer. But it's important to stress that we are not looking only at the elastic modulus or the viscous modulus, but also the yield stress and the yield strain in order to understand the toughness of the material. Not only at the beginning when we are looking at the printability of the ink, but also after this, in order to predict somehow how the structure will behave afterwards. Okay, a bunch of plots full of data. I'll try to navigate you through this data. You can see here our equipment, and you can see, first of all, that the data below a strain of 10 to the power of minus 1 are quite messy. So what I suggest you to see is something that is above this strain. This is both related to the, let's say, to the limits of our equipment, but also to the stability of the inks. In these plots, and you will see a couple of slides of this kind of plots, you will see the data for bovine and fish collagen, of course mixed with hydroxyapatite, with 2 days, day 1 and day 6, because we also wanted to see how the ink is stable throughout the time. Because what we know is that when we are printing the ink, the material will behave in a way, but we don't know exactly if we leave the ink for any reason, because we want to do something else, we leave it, let's say, at open air, how it will behave after a couple of days, or so on. And we see that for the fish-based source, basically we see a more stable behavior. You can see that basically the curves are overlapping. So the fish source is much more stable than the bovine one. As for the numbers, I want to show you the numbers compared to other plots. So I'm adding data. I'm sorry to keep you looking at this, but just look at the arrows. Just follow me. So you can see that the order of magnitudes for our inks are similar to the first plots, in which I'm showing you other similar studies. These are unpublished data, in which we are using only HA, and HA alone has been 3D printed for a very long time. And we know that using only HA, we have a very strong, although fragile, material. But the very nice thing is this one, because the notches and, let's say, the main values, especially here for the stress, are more relatable to these other plots. And these other plots are related to an ink in which we are also adding silk. That is another, of course, green material. What does it mean? This means that, especially here, looking at these plots here, we have a strength that is similar to the HA, but a yield strain here 10 to the power of 0, that is similar to an ink that is similar to the one in which we are putting silk. This means that we are expecting an ink that has a very high toughness compared to the single use of hydroxyapatite alone. So we are basically increasing the properties that we observe with silk, and we are expecting collagen to have, let's say, a better behavior with respect to silk. That is another material that is much cheaper. Of course, it's much cheaper, silk, although you have to process it through a lot of chemical steps, but it's much cheaper. But we can use collagen not from human sources. We can use collagen from animal sources. That is cheaper too. So let's say it's a win-win. Looking instead of these other plots, we are observing here the behavior throughout a frequency range. Maybe you are asking yourselves why we are doing this kind of study, because for 3D printing applications, we are only looking at the parameters versus strain. But why we are doing this? We are doing this because this can be an application. And this is, let's say, I'm very affectionate to this kind of application because it's been my framework all along. So we can create, with 3D printing, prostheses. Here you can see a prosthesis that are replacing the ossicles of a ear. And in this case, also the behavior of a material throughout the frequency can be very important. As you can imagine, all the stuff that are occurring here are all related to frequency. So having also characterization throughout frequency can be very important. Especially here, looking at the viscosity. A viscous material means what? It means that the material can dissipate energy. And it's very important for, let's say, an hearing-related application. We don't want to have our organ hurt by some energy content that is very high. So having a material that can dissipate, especially at high frequencies, let's say the energy contents can be very, very important. And it's just an hint of what we can do. And here, let's say, the next part, and this is ongoing, as I told you at the beginning. Here you can see the material, here, bovine, here, fish, and here we are waiting for a complete solidification of the samples. I cannot show you the mechanical properties of the inks right now because we tried to 3D print immediately the samples but unfortunately we saw some collapses, so we say that, okay, it's not properly, let's say, we cannot follow the right, let's say, the right rules for making the mechanical test. So we are trying a different approach. We are trying to make them solidify, let's say, in a fixed structure. Then we will destroy it. We will destroy it, so it's a destructive test somehow. We will destroy, of course, the plate. And then we will use this to make our mechanical characterizations, of course, compressive mechanics. So, as for now, we carried out a complete understanding. We have a complete understanding of the rheological properties of marine source and bovine source-based inks for 3D printing application. What we need to do is the correlation between the mechanical properties and printability. But unfortunately, I cannot do this until the end of July. So somehow this conference was, let's say, organized a bit earlier than expected. So probably next time I will present also these other results. So I'm really sorry I cannot show you the final results, but I'm sure that next time I will speak about them. Thank you for your time.
Thank you very much for your presentation, Mario. Any questions? Yeah.
Hello, Andreas Steper from Fraunhofer, Germany. This might be a stupid question, but I don't have any medical background.
There are no silly questions.
Is there any data on the biocompatibility of fish and bovine collagen?
Yeah.
So which one is better or doesn't matter?
As for now, we can say that the fish-based collagen is better for 3D printing application, also because it presents, let's say, more stable behavior with respect to the bovine one. That after 6 days, already after 6 days, let's say we have a drop of the mechanical properties. So, but this has to also be confirmed because by mechanical characterization tests, because what we are looking at this, we are predicting the behavior with the printability, but we cannot say anything about the final behavior, let's say Young's modulus and compressive strength, because once we will get the samples, of course, much of the solvent will evaporate. So we have to understand how this lack of solvent, let's say, of course, will affect the mechanical properties of the inks.
Thank you.
You're welcome.
So very nice work, Mario. Always a pleasure to hear you. The silk data that you were showing, that's not yours. That's someone
No,
has.
it's mine.
That's yours. So what silk are you using?
It's already been submitted, so we are waiting for from the reviews.
But which are you taking the fibrin, or what part of the silk, or the whole
fibrin.
thing? The fibrin. Okay. And you isolate it yourself, or you buy it, or?
No, I isolated.
You isolated from cocoons and all that. Oh, nice.
At Kaplan's lab, Tufts.
Sorry?
At Kaplan's lab.
And Kaplan's lab. I see. Okay.
Because that is a work in collaboration with Tufts University and MIT.
I see. Because we're doing some silk as well, so we should talk.
Yeah. In that case, we were studying the effect of the plasticizing effect of silk in HA water inks. So changing the amount of water, changing the amount of silk, how this will affect also the printability and the stability of the inks.
Oh, right. Yeah, we're doing some inkjet printing of silk at the moment. Yeah.
Hopefully I will send you the paper once it will be revised.
Fantastic.
Hopefully.
Great.
We're still waiting. After 2 months, no news.
Oh my God, okay. You've targeted a very nice journal, I'm sure. Thank you.
Thank you.